Okay, so yesterday we discussed photons following geodesics, and we discussed today we'll discuss photons following geodesics. Yesterday we defined the form momentum of a photon to be this, where lambda is an affine parameter. What does it mean for lambda to be an affine parameter?
Right-hand side of the
It means that the photon satisfies this equation. Oh. Equals 0, and this will remain true if I scale the parameter or shift it by a constant, but if I do anything else to it, this won't remain true. Now, few people have asked me how to derive this equation, and that's a valid question, because I derived it from some action in the massive case, and we can't derive it from the same action in the massless case because the quantity g mu nu x dot nu is simply 0. So actually we have an additional equation, this. This is a quantity which was non-zero for a massive particle, but it's 0 for a photon. So there is a nice formalism, but it's a little advanced to do it in class here. It's not difficult, it's just maybe not necessary. You can just assume these equations. But I can put in the notes as an advanced exercise, optional for people who are interested. Whoops, that was not good. Can people still see the thing? And is it visible also in there, in the video? Video will adjust the light, I think. Okay, I'll continue then.
So we claim that the photon's geodesic is also the
Yeah, we claim this, but I can give you a derivation which is uniform for massive and massless particles, which will land on this equation for both. Okay, so now our task is to calculate the path of a photon in the Schwarzschild metric. And it's obvious why we want to do that, because this will give me a prediction for how light behaves when it passes by a star or a planet. That's something that we can hope to measure. Now, one thing you could do is say, well, we have done this calculation already for a particle of mass m, why shouldn't I be able to take m to 0? And that's a reasonable question, and in fact it can be done, but it's a little tricky. Maybe actually what I can do for you is to do that derivation here and leave the more direct derivation for you to read from the notes. While in the notes I've done it the other way. I've given a direct derivation for light, and I've asked you as an exercise to look at the massive case and take a limit. So let me do it that way, because I think it's also fun to do it that way. So recall that when the mass was not 0, we already found this radial equation. How? By setting u mu equals minus c squared, and satisfying this equation. Well, we didn't even need this. We just actually plugged in the killing vectors into this and got a radial equation, the conservation of energy. And that equation was half m r dot squared minus gm m by r plus L squared by 2mr squared minus gm L squared over m c squared r cubed is equal to e squared by 2 c squared minus m c squared by 2. And what we want to focus on now is the small m dependence. So we imagine that small m is getting very small, tending to 0. And what do we find? Well, this term and this term, sorry, I've done something else wrong. No, sorry, here, yes, there's an m here also. What was the comment? Something?
I said it blows up.
Blows up, yes. This term and this term blow up. This term and this term go to 0. Doesn't look very good. However, you can do the following thing. First, multiply throughout by m. And you'll get half m squared r dot squared minus gm m squared by r plus L squared over 2r squared minus gm L squared over c squared r cubed is equal to e squared over 2c squared minus m squared c squared over 2. Just multiplied everything by m. Now it looks a little better because nothing is blowing up when I take m to 0, but there's still a problem. I want an equation for r dot, because that's going to be integrated to tell me what is r as a function of lambda, and that is the actual path of light, and it doesn't look very nice if m is taken to 0 in this. But here we remember something. So let's do the following. We are free to rescale the parameter. Remember, this was all done with proper time, and that is why this confusion. This dot is proper time. So what we are going to do is replace the proper time by a parameter which is m times lambda. So tau goes to m lambda. In that case, the first term becomes half r dot squared, where this dot is with respect to lambda. The remaining terms just are as they are. Okay? And now, once I have done this, this term is not going to go away, and now it is properly parameterized in terms of an affine parameter, which is not the proper time. Moreover, we see that by this action, if this had dimension of time, this has dimension of time by mass. And we saw that that's exactly the dimension lambda should have in order to make the form momentum have the dimension of form momentum. So everything is good. And so now we can do this, and now we see that when m goes to 0, this term disappears and this term disappears, and all the other terms are finite. So I write and it turns out that this is indeed the correct equation for the photon in the Schwarzschild metric. Okay, it just loses a few terms. Of course, we can see also why it's losing those terms. Obviously, this term had something to do with the rest mass of the original particle, mc squared, and that's 0, so it should go. And this term was related to the Newtonian force between the particle and the planet or whatever. M was the planet and small m was the particle. But of course, this shouldn't be there. Newtonian physics has no real room for a force between a massless particle and a gravitating object. Despite that, let me say that there is a famous calculation of bending of light in the field of a planet, which is done by somehow some kind of assumption within Newtonian physics, and it actually gave an answer. So, but in my opinion, that derivation is just not valid in first place, even in Newtonian physics. But okay, you can look it up. ChatGPT will summarize it nicely for you. But we are going to do the true derivation in actual gravity, and we'll get the correct answer. Okay, yes?
So tau is 0 for light and the other.
Yes, exactly. But m is also 0. So I'm going to take tau, replace tau by m lambda and then send m to 0 afterwards. It's reasonable, so tau is actually going to 0 as desired, but lambda does not go to 0, doesn't have to go to 0. Okay. So that's the light equation, and now we just have to sort of solve it and find trajectories. And for this, okay, so the first thing we can do is rewrite it nicely. So this has a nice feature that it can be, it can be written as half r dot squared plus v of r is equal to e squared by 2c squared, where v of r is just these two terms, but let me factor out L squared by 2R squared from them, and then I immediately see that this is nothing but 1 minus RS over R. So this Schwarzschild radius has made an appearance in this formula. It was already there in the massive case, but there was also a Newtonian term. Now there's no Newtonian term, so this is the actual potential. Okay. Needless to say, we don't have to worry that the potential will vanish at R equals Rs, because we cannot reach R equals Rs for a normal planet or star or even a neutron star. Earlier we were worried about whether we can reach 3 by 2 Rs. That we might reach for an extreme neutron star, but we are certainly not reaching Rs itself. Okay, unless the object is a black hole. No non-black hole object in nature, as far as we know, has has its matter of the same size as, exactly the same size as Rs. Okay, good. Fine. So now let's, as we did before, the procedures are very simple and we can do them very fast. We have to first look at the shape of the potential and identify what are turning points, stable points, unstable points. And it's very, very simple in this case. We simply plot this potential and we find that it looks like this. So it has no minima, but it has a maximum. This is R, this is V, and the maximum comes by differentiating that and setting it to 0. And interestingly, it arises at 3 gm by c squared, or 3/2 times the Schwarzschild radius. Okay, and this is a famous, okay, have I done this right? I hope I've done this right. 3, yes, this is correct. Good. So we see that actually the only chance for there to be a circular orbit is at this point, but it's necessarily unstable. If it's perturbed slightly, the photon will fall into the body, into the planet or star, and if it's perturbed slightly the other way, it will go out to infinity. But it's still important actually, and turns out to be important even observationally. Now what's the height of the barrier? We just have to put this value into this expression and evaluate it, and we find that V at R equals 3 gm by c squared is equal to 1 by 54 c squared L by gm whole squared. A simple calculation. And now this is supposed to be, this is V, and the total energy that we start with is this right hand side, E squared by 2c squared. Okay, so if this energy that we assign the photon is larger than that height, then the photon will just fall into the star, and if it's smaller, then it will come up to here, be reflected at this point and go back. So that's the turning point. Okay, clear? Good. So to analyze this further, it's very convenient to define a quantity with dimension of length called the impact parameter. It's something we use in particle physics. If I have an object which I'm trying to hit with another one, which is what we do in particle physics, then imagine one of them is at rest, and imagine the other one is in a beam which is moving like this, then the closest distance of that beam to the object at rest is called the impact parameter. And we do exactly the same experiment that we want to do now. We'll actually determine the angle of deflection in a scattering. This can be a scattering of two nuclei, or it can be two protons, or a proton and electron. That will affect which way the beam bends. But this is how particle physics is done. You have had a course in particle physics, nuclear and particle physics, which I hope has discussed these things. Good. Okay. So what's the impact parameter in this case? So we write it as CL over E. This is a quantity with dimensions of length, and it's the natural one which determines how far this beam is passing from the center of the planet, which is at r equals 0. So now the condition for crossing the barrier, so infall condition, it's clear that infall will happen if B is sufficiently small, because if B is very large, it's going to miss the planet altogether. It can't fall into the planet. If B is very small, what's the actual light ray or particle going to do? If it's coming like this at small b, it will bend round, and it may, if it's sufficiently small, and b is really small, then it will bend round and it will eventually land inside. It's not going to go straight in, obviously, unless b is 0. But if we look at only the radial equation, which is the only equation we are studying, then we simply see that the distance of the point from the center is just steadily decreasing. Okay, because we understand that the angular equation will make the angle also evolve with time, so it's going to curve round and crash inside, right? So that's what we expect for infall. And for that, the energy should be above. So the energy was E squared by 2c squared, and this should be greater than 1 by 54 c squared L over Gm squared. So we can take this 2 to the other side. This is 27. Then we can take a square root, and we get E by C is greater than 1 by 3 root 3 c squared L by Gm. Okay, all good?
Could you
Yeah.
explain the condition for the reflecting back that you said a while ago? I did not understand that.
When I have a barrier like this, if a particle comes in to a potential barrier, it's reflected back. This is classical physics. We're not doing quantum physics. In quantum physics, it can also tunnel through, and that may also happen. But that's not what we're doing. We're just asking what a classical light beam does. But it's anything. I mean, in this case, we know, because GR has very precise rules for light beams, that even a light beam will do that. But in general, if you have a potential like this and a particle coming in from infinity, this is, remember, a diagram of energy against distance. So particle has a fixed energy. That fixed energy is such that, so here its kinetic energy plus potential energy is fixed. Always it's fixed. As it comes here, the potential energy is growing, so kinetic energy is tending to 0. As it reaches this point, its kinetic energy is exactly 0, so it comes to rest, and then it goes back. Now for a photon, that's not exactly what happens, but that's not important. The point is, we are only asking whether it goes in or it doesn't go in. Okay, we are not solving a classical, we are not solving T plus V, we are solving some effective equation. In the effective equation, everything is well defined. Even the mass is 1 in that effective equation. So we are not trying to understand exactly what's happening to the photon, but we can be sure that, okay, so first of all, try to understand that the photon doesn't have to come to rest if it reaches here anyway, because this is only the radial equation. In the angle, it's still turning. So the actual trajectory is what I drew. I mean, it will, so the actual trajectory in the case where it's not infalling is like that. There's no reason for it to come to rest. But if you see the radial distance from this to the origin decreasing up to here, and in a sense it comes to rest here. That is, at this point r is at its minimum, and then it starts increasing again. That's what this is doing. Yeah.
Is there a shift in the wavelength of the light because of this?
No.
Because the energy, if you want to conserve.
Okay. Sorry. Good. So there may be a shift. Yeah, we have it actually tomorrow. In tomorrow's lecture, I'm going to talk about gravitational redshifts, and yes, there will be a shift in the wavelength of light, but it will be see, light is coming in from here, light is going out there. Okay. Over here in this field, the wavelength might shift, but we are not really worried. We are not trying to detect the light here anyway. We are trying to, actually I'll talk about what we are trying to detect. Let's just finish the conditions for light to fall in or not fall in. Okay. And the infall condition is energy should be sufficiently large, and we can recast this in the language of that impact parameter by taking things to the other side, except that my C factors, no, I think this is good. Yeah, this is good. So this is the same as saying that CL by E is less than GM 3 root 3 GM by C squared. Good. And this quantity GM by C squared is half the Schwarzschild radius, which was 2 GM by C squared. So this is equal to root of 27 by 4 RS. So there's a number, root of 27 by 4, such that if the impact parameter B is less than that, then it will fall in. And B greater than 27 by 4 RS, no infall. Instead we have bending. I hope it's clear. There are two possibilities and they are decided by the value of B. People are not, I think I discussed them separately and that might be confusing. Let's draw it. Infall, light coming in, planet here, light goes in and goes in there. No infall, but bending. Same planet, same light, except that it comes in with a different impact parameter, maybe a little larger one. And it goes there. Okay, is it? Sorry?
There should be a third case as well, right?
What is it?
That B is exactly equal to 27 by 4.
Yeah, well,
It's the unstable orbit, right?
yeah, I believe that's the unstable orbit. We already saw that there's an unstable orbit, circular orbit. So yeah, that is there. But that's not interesting for light coming in from infinity. I mean, it might be in practice, but that's okay. We are. My point is that we are trying to calculate this. Can you please not try to make me do other calculations? This is what we want to calculate. Why? Because people spent years to measure it. Okay, so let's focus on calculating this thing. We are only trying to calculate the infall condition so that we know what is the condition where this takes place, which is B greater than that. Now, what is the physics of that? B greater than some number which is of order around 2 or 3 times the Schwarzschild radius. So that's that essentially means that unless you aim the light directly at the center of the planet or star, it's not going to fall in. No, it's simply a question of aiming. It has this thing. It doesn't really depend on L or E. It depends only on the ratio CL by E, which is a quantity of dimensions of distance. Okay, so if you want the light to fall into the sun, whose Schwarzschild radius is there, you actually have to send it so that if nothing was happening, it would actually land there. Okay, so again, we are working with the vacuum solution and we can't even really believe this calculation because at some point the light will enter the sun and after that we don't know what happens because then we have to resolve Einstein's equation. I've told you this many times before. However, what we know is that outside the sun there is vacuum and light which is going like this will definitely bend. That's what we have proved. It won't fall in. That's what we need for the rest of the calculation. Yes?
I'm sorry, this might be taking you off course, but L was defined in terms of small m again.
What was?
L.
L. No,
The
L is
envelope.
just the conserved. No.
Yeah.
Good.
In massive case.
So all that was scaled out when we rescaled the affine parameter. And if you look in the notes which I'll post today, the L in the case of light has is the same formula but with m replaced by 1 for the same reason that P was defined as m times u where m is replaced by 1. It's not that m is actually 1, but that m is replaced by 1 and tau is replaced by lambda.
I see. Thanks.
It's basically that idea. So actually the killing vectors are slightly, I mean the conserved quantities are slightly different in the light case. They have no m in them. So what I said earlier was that actually I can do the first principles derivation of that equation, the potential for light. And to do that, I'll already start with the affine parameter instead of tau, and I'll land on the same equation which I did. Okay.
Thank you.
Good. Okay. So anyway, I think there were there was a lot of distraction in getting to this, but I hope the point is clear that B is, in order to be in the vacuum solution, B has to be greater than this. There is no B which is less than this and doesn't encounter the vacuum solution, the non-vacuum solution, because the body that we are dealing with is always larger than its Schwarzschild radius. So if we want to study infall of light into a planet, Schwarzschild solution is not going to tell you the details of it. Okay? If we want to study no infall but bending, that is generic. Any light which is grazing the surface of a planet will generically bend round. If it is not grazing the surface, then it will enter here and after that we are lost. We don't know whether it will exit or it will orbit or what it will do. So let's stick to the thing that we know, which is that if B is greater than this, it will bend around if B is outside so this is B, outside the matter distribution of the star, it will bend, and it's what we want to calculate. And it's quite a tedious calculation, so let's now actually get down to it. I hope the equations were clear. We simply calculated the potential, we minimized it, rather we made it stationary, calculated the height of the barrier, and then argued that the energy on the right side of that conservation equation needs to be greater than that for infall, which means the energy is large compared with the angular momentum, which is the same as saying that B is very small. And then if B is the other side, that is it's sufficiently large, then there's no infall and we can calculate the behavior. Okay. Now we had an orbit equation, if you remember, which was obtained by eliminating the parameter, proper time in that case and lambda in this case, between the radial and the angular equation. And the orbit equation was d r by d phi squared plus 2m r fourth over L. So massive case, it was 2m r fourth over L squared V of r equals 2m r fourth over L squared E. Okay. What is it in the massless case? Well, it turns out that it's exactly the same, except that m is not there. How do you find this? You just have to look at the angular equation, and I wrote you the radial equation, eliminate lambda between them, and you'll get this. So in the massless case, you get this. And this V of r is the one that I had written down, which was that factor times, yeah, it was, let's keep it somewhere, L squared by 2, this was L squared by 2r squared, 1 minus rs upon r. Okay. And so this thing plus that is equal to, now what's on the right hand side Again, there is no L, and it's not directly E. This is actually E squared by C squared. E squared by 2C squared, or E squared by C squared. 2C squared. Okay. Good. So now we want, since we know that we are looking at bending of light, we can ask for what is the point where the radial function turns round, which is just the turning point as I showed you in the picture. This is the potential, and this stops here for a given value of E squared by 2C squared, and this, let's call this R0, the turning point. We can easily calculate that. These are all trivial classical mechanics calculations. And the answer we get, so this happens when this is 0 and this is equal to that. Okay? And if you equate these two things and solve for R0, so you will get L squared over 2 R0 cubed, R minus RS is equal to E squared by 2C squared. Okay? So, let's see. First of all, we equated these two, so we could drop the, I think there's an L squared here. We could drop the L squared and the R to the fourth and the 2. And then we simply equate these two things. I'm just worried about the, yeah, this is correct. So what I did was to take this one more R out. So I got R cubed and here R minus RS. Okay? Okay. So now let's rewrite this equation and try to integrate it. So this equation gives me, so now you know that, sorry? Yeah. Okay, so now you know that in the previous case when we did the massive particle, U equals 1 over R was a useful quantity to define. So we do that again here. And now the equation becomes RS U0 cubed minus U0 squared plus 1 by B squared equals 0. And this is the equation that determines the turning point. So the solution of this equation is U0. Okay, it's a cubic equation. If it was a quadratic equation, I would be able to solve it readily, explicitly. But it's cubic, that makes it a bit harder. Notice, by the way, that the limit of no planet or no star is when RS goes to 0, right? Because RS is proportional to M, the mass of that star. In that limit, we certainly know that U0 is just 1 by B. Okay, and why is that? It's very, very simple. Here's the star that now I have removed. Then what is the point of closest approach of this incoming particle, which is actually going in a straight line? There's nothing there, so it's not deflecting, right? But the point of closest approach is 1 by B. I mean, R is equal to B. So U is equal to 1 by B. So that this confirms that we are doing the right thing. Question is how does this cubic term modify that? Okay. And that will, so now if we want to integrate the radial equation, the orbit equation, which is that one, it's very straightforward to write. It's not very straightforward to evaluate. So let's try to integrate it without M. So from this, by taking all that to the other side, we get dr by d phi is equal to L by R squared 1 over root of 2 E squared by 2C squared minus V of R. Okay, I have a slight, I think I have a slight inconsistency. This is not E but E squared by 2C squared. We always keep this as the quantity which stands in for E. Okay, so this is the quantity. And now we can easily simplify this by inserting explicit expressions for V of R, cancelling some 2's and all that. And we eventually get, so this 2 will cancel with that 2. And finally we'll get 1 by R squared, 1 over square root of 1 by B squared minus 1 by R squared plus RS over R cubed. As usual, the troubling term is that. Okay, and again we'll recast this in terms of du by, well, to solve it, okay, we have to solve it, but you can see that there's an equation that now I can integrate. I simply take phi to the other side and I have dr upon this function of r. That will give me the orbit. If I know the orbit, I know the bending. How exactly do I know the bending? So this is a little tricky. If you think of the angle of an incoming beam bending around the planet, this is the center. So the angle is that how to say it? So here the angle, so this is one line, and then when I bend and go there, I have a different line which connects there, and this is the amount by which the angle has actually changed. But I think I've got it wrong. Let me try to draw this better. So
It has to be parallel to that. So
yeah, sorry, what has to be parallel? So the first thing I wanted to say is if there is no planet, then it's a straight line and the angle is simply pi,
yeah.
okay, with respect to that. So this is pi. Now what will happen if it, actually this is the angle which is pi. And what will happen if it bends is that the angle is greater than, this is what I was trying to do, thank you. So the angle, this angle becomes greater than pi if it bends, okay. So we will define delta phi to be the integral d phi by dr, that's going to measure this entire angle, and then we define small delta phi to be capital delta phi minus pi. In the no deflection case, delta phi should be pi and this delta phi should be 0. That's when there is no planet. And when there is a planet, this delta phi should be greater than pi. This is how it bends. Okay, so the discrepancy between that and pi will be a small quantity. We know it's going to be small because general relativity quantities are always small, and that's the one that we'll want to measure. Okay, so that's delta phi. So if we set that up as an integral of this, we get delta phi is equal to integral d phi by dr, and that's equal to integral dr upon all this stuff, r squared and this root 1 by b squared minus 1 by r squared plus rs over r cubed.
This one is downward, no? Ulta.
What is ulta?
D phi by D, dr by D phi and D phi by D.
Sorry. So what do I have here? Delta phi is actually d phi by dr, yes. Oh, did I write it wrong to start with? I think I wrote the wrong thing. No, I had it. No, this 1 upon came by writing d phi by dr. This is d phi by dr. This is d phi. I just wrote this one wrong. So what I did was to take the equation for dr by d phi squared, take everything to the other side, square root it, and take 1 upon that. Then you get this, and you get this. Now this is not, and okay, what is the integral from? So here is a problem. The integral is actually sort of from minus to plus infinity, but that doesn't tell us very much. It's actually from, you can break it in two halves, from minus infinity to here and from here to plus infinity. Okay, and it's double of that because this orbit is perfectly symmetric between this part and that part. Okay, the incoming part and the outgoing part. Okay, so it's actually, I can put a 2 here and do minus infinity up to turning point R0. And R0 is determined how? By the fact that it makes this square root vanish.
Shouldn't it be plus infinity to R0?
It's minus infinity to plus infinity, so it's minus infinity to R0 and R0 to plus infinity. So either of them is correct.
Negative R is not a part of our coordinates, right?
Of course it, I see.
It has to be R0 to infinity.
Sorry. Okay, so yeah, good point. Yeah, I think this was not the correct way to write it. I think it's just directly, yeah, thank you. It's directly 2 times the thing from R, yeah, okay. So what happens is that this part, yeah, you're right, this R cannot be negative. This part R is positive, this part also R is positive, and both are from R0 to infinity. And they add up because each of them, the deflection is the same. The deflection for this is up to here, and then this tangent vector relative to that, that's the deflection. And then from this, when it continues, it continues bending, and then it's between this tangent vector and that. And both are the same. So this is the correct answer. Thank you. Okay, and this we can recast in language of U, which slightly simplifies it. And then we will get a little stuck, and let's see how to do. We'll have to do an approximation. But at least up to this point, we can do it. So it's 2. This now integral becomes 0 to U0. So this, when we do R to 1 by U, this becomes minus 1 by U squared. That eats up this factor. So that's 1. This becomes U0, and this becomes 0. But there was a minus sign in the change of variables, so we flip them and we get 0 to U0 du. And we simply need to write down the denominator here, 1 by b squared minus u squared plus rs u cubed. So it's at least as simple as it can get. And now again we can do a little exercise to make ourselves feel sort of confident that we are on the right track. Supposing again rs is equal to 0, then this integral is a simple one, right? Du upon root 1 by b squared minus u. Moreover, u0 is 1 by b. With a simple change of variables, this will then become twice integral dv over root 1 by minus v squared. Do you know what this integral is? Sine hyperbolic, sine inverse.
Sine inverse.
And what is the value of this from 0 to 1?
Sine inverse is
Pi by 2. And so 2 times pi by 2. So does this agree with the prediction? It says that the scattering angle is pi. I mean, not scattering angle, but the delta phi is pi if there's no planet. Okay. So now we are confident that if we do this thing in the limit of small rs, we'll actually be able to get a deflection. And limit of small rs, you might think the best thing is to just expand out this and take it up, but there's a little problem. The problem is that u0 is a solution of this. Okay, so this depends on rs, and and if we naively just take this up, then we don't know how to do the integral. So there's a cleverer method in which we approximate it slightly differently. So let me run you through that. So first of all, we write, so this is delta phi, there's a 2, there's 0 to u0. So first of all, we redefine u equals v by b. Okay. So then the integral will be and let v, so v0 is equal to b u0. So now it will be from 0 to v0 dv upon square root of 1 minus v squared plus rs upon b v cubed. We learned something already by this without doing the integral, which is that whatever the answer is, it only depends on the ratio RS over B. What is that ratio? It's a physical quantity. Schwarzschild radius over impact parameter. What is the typical impact parameter? The closest light can get to a planet is the boundary of the planet itself. So it's RS over what we had earlier called the physical radius R0 of the planet, which is going to be a very small number. So we are quite happy that this will be small. The correction will be small. Okay.
R0 isn't the radius of the planet, is it?
Is a physical R. Oh, this, sorry, there are two R0s. Earlier in the course, we had an R0, which was the physical radius of the planet, not this one. Yeah. Yes. That one's gone now. Now we have V0. Okay. So the trick in doing this is actually called a frequency shift method, and I had to sort of relearn it myself. It's not completely straightforward. What we do is to rewrite this factor as V squared into 1 minus RS over B V. This is our factor, right? We just factored out V squared. And now I'm going to write this as square root of 1 minus RSV over B times square root of 1 over 1 minus RSV over B minus V squared. Is this step clear? This is a factor multiplying V squared. If I take it out of the full square root, it comes out and I get 1 over that factor from this and just minus V squared from there. This is a simple change of, this is not even a change of variables, it's just rewriting. Now what I will do is to approximate everything to linear order in RSV over B. So this will become 1 plus half RSV over B. This, I'm taking it up. This is 1 minus something to the minus half. So it's approximately 1 plus half that thing, Taylor expansion, and there are no other terms. I'm keeping only linear terms, fine. And that one I will write as downstairs, there's dv here. And downstairs I'll write this as 1 plus RSV over B minus V squared. So I approximated this thing by 1 plus the same thing. 1 over 1 minus epsilon is 1 plus epsilon. And so I got this. Now you see we are in much better shape because we've kept the RS over B correction, and now the square root is quadratic because of this approximation we made. So actually it's not difficult now to think of the turning points of this. The station, I mean the points where it vanishes. And so now we can actually look up the integral. In this form, the integral can be looked up. All you do is you ask any table of integrals or AI that do the integral 0 to V0 dv 1 plus alpha V divided by square root of 1 plus 2 alpha V minus V squared. You agree that that's that integral where alpha is equal to RS over 2B. Yeah. So we just ask for that and we get an exact answer, but of course we are not supposed to take it the full answer because this integral is only valid for linear order in E alpha. So but I'll take the full answer and approximate it to linear order. So first let me write down what the answer is. Just to show you the importance of being careful and looking at details. So predictably it's a sine inverse type of integral. Now how do I make the linear approximation? Tell me step by step, what do I do with this term? Alpha square term should be ignored, very good. Here and also here and also here. So this term gives me pi by 2. This is just alpha. What's the last one? So what is that to linear order in alpha? Yeah, it's alpha. I mean, sine of alpha is alpha, then sine inverse of alpha is also alpha for small alpha. So it's pi by 2 plus 2 alpha. What do we have to do now? We have to insert alpha, but we also have to remember that the integral of interest to us has a 2 sitting in front. So we'll go back up here and write this as 2 times pi by 2 plus 2 rs over 2b. That was alpha, which I just erased. So it is pi plus 2 rs over b. This is our final answer for delta phi. And therefore delta phi is 2 rs over b. And now it's a matter of putting in numbers. So how do I put in numbers? First of all, what experiment am I proposing? So let's be clear about that. So I want to do deflection of light around the sun. So sun has some rs, which actually we know it's just 3 kilometers. It's very small. Okay. What is b? Now here the crucial question arises, how are we going to observe bending of light? By the way, notice one thing interesting, unlike a matter scattering where I have to send in a beam of some bunch of matter and scatter it, light is ready-made. Light is coming to us from stars all the time. We don't have to create it. So if light is bending around the sun, it's already bending around the sun, whether I'm looking at it or not. It's not an experiment I need to do. I just need to find out where I should go and how I should look to see it. So tell me how you would see bending of light around the sun if the light is starlight.
Yeah.
Let's try to think collectively, huh? In an eclipse, excellent. That's the first observation, that if I'm here and this is the sun, then I better not be trying to see light bending around it, because it's going to blind me as well as all my equipment as long as the sun is shining. So I need to wait for a total solar eclipse. That's not very easy, but very luckily such a thing was provided by nature sometime in 1919 or so. Good. So eclipse. Okay. So what do I look at during the eclipse?
Stars behind this one.
Stars behind the sun, somewhere here. And what light should I be looking at? I'm getting there are stars everywhere. All their light is coming to me.
Their apparent position.
I should look at the apparent position of a star whose light is grazing the sun and coming to me, right? Just grazing the sun. Because that's the one which will be closest to the sun, and what will be the impact parameter of that? Radius of the sun. Perfect. So B is equal to radius of the sun, which we know pretty well, and it's equal to 6.96 times 10 to the 8 meters. Okay. But we haven't finished with the experiment. Once I look at the light coming from the star and I find the apparent position, what should I do next? Compare it with something. What?
At the night, look at the stars.
Night.
Maybe.
Well, the same. If the star was behind the sun in the day, at least that night it's not going to come in front of the sun. Huh?
6 months later.
6 months later. Very good. Very good. So this experiment takes many months, and that's exactly right. So let me also prepare you for the answer. This experiment was done in 2 parts. Eddington and Dyson, who is not related to Freeman Dyson, different Dyson, James, I think Dyson, planned the expedition in 1919. And the idea was that Eddington will go with the expedition to West Africa, where there's a small country still there called Príncipe Sao Tome. These are Portuguese colonies. It's one country now, and it has 2 islands separated by a few hundred kilometers. So they picked this island. It's a tiny island. apparently was a good place to view the eclipse. Now I can't go in, I don't know the details why it was the right place to view the eclipse, but obviously when there is going to be an eclipse and we know how it's going to look, then we can find the right place on Earth where it is most visible. Dyson, however, went to a place in Brazil. Actually, he didn't even go. His expedition went to Brazil. He stayed back in England and somehow organized it from there. Don't ask me how, without internet. But he somehow did. And so they took some telescopes with them to Brazil. These guys took some telescopes with them to Principe, and they tried to do the observation. As often happens, they were dogged by different problems. The telescope that they took to Brazil, large one, just went out of focus because of the change in weather and could not produce any reliable images. They had a smaller one which remained in focus, and they used it. These guys, on the other hand, had clouds. The perpetual problem of eclipses is that just on the day when you want to see it, and there isn't any more eclipse going to happen for many years, turns out to be cloudy and you're basically sunk. So they had clouds, but they got some kind of observations, but not maybe as good as needed. And also they had to stick around in these places for many months later to wait for the stars that they had been seeing to be visible at night when the sun is not there, and then when their light is not deflected, and then compare. Okay, that would give them the deflection. Okay. So now if we calculate this quantity, you know the procedure. We first get an answer in, yes. Yes.
When you are observing the light,
Yes.
from the angle which you are observing, you will know that this is the light which is coming just grazing by the sun.
Grazing by the sun. Well, actually in an eclipse you can still see the sun. It's just a dark sort of shadow. So you can actually, and you're seeing starlight all around it.
But experimentally, you will just see a difference of angle, and then you will say that. Okay.
No, the light is actually coming from next to the circle of the sun, right? I'm here and I'm scanning the sky in the direction of the sun, and obviously the sun blocks out starlight which is directly behind it. But as soon as I come to the edge, I start seeing starlight from the edge onwards. So I just take the one which is closest to the edge, but I have to find out what star it is or stars. So and note it down so that few months later I can identify the same stars and find their angle of their light to compare. Okay, then you know the story. I have to take this ratio, but I'll get an answer in what units? Radians. And then I have to convert to degrees, minutes, and arc minutes and arc seconds. And in the end we get, and then of course I have to also, that's that quantity. So this is 8.49 times 10 to the minus 6 radians, and this is 1.75 arc degrees, one of the most famous numbers in history of science. What did Eddington and Dyson find? So they had large errors, probably because of the clouds. So their answer was this. And Brazil people had smaller errors, but they had a small telescope which might have introduced some systematic problems. So they got this. And within the, okay, it's true that even at its lowest, this comes to 1.82, which is a little higher than this. But, these are experiments from more than a century ago. They have been repeated since then many times in many other ways. And it has converged on this answer. So now the problem is that the fake calculation of the same deflection from Newtonian physics apparently gave 0.86 or so, about half of this answer. So there was a lot of confusion, and this is always the case when, new science is being done. There's enormous confusion. First thing is that Einstein calculated, I think he calculated using some, Einstein developed, as we've told you many times, general relativity over a period of 11 to about 15. He spent actually really 10 years thinking about it, but especially the last 3-4 before the final paper. 1915 is the paper, but he had papers before that which allowed him to do certain calculations without having got the final theory in its final form. And he, I believe, also came up with something like half of this value. Okay. Now the problem is that in between that and 1919, when this was done, people did try to do measured bending of light, because see, measuring bending of light has nothing directly to do with any theory. It's a astronomical observation that anybody would, really deserve a Nobel Prize for doing under difficult conditions with that with the equipment they had. And so they were trying to do it, and if they had measured it correctly in 1911 or 12, it would have been very confusing, because Einstein already had only half of this answer, and then they would have said that Einstein is wrong, and then this expedition might not have happened, because by this time everybody was screaming that Einstein needs to be verified. So luckily the expeditions in 1912 to 14, that range, they all failed for one reason or another, again weather and also some, I think, World War I and so on, and this was the successful one. But luckily by this time the prediction from GR was unambiguous. In 1915 was the GR paper, but took some time for people to really understand what is the precise prediction, but the calculation is what I did here, and that's the answer. Okay. So moral of the story is, it's really worth the struggle to get a right answer and a right answer from theory, and also to measure the thing correctly. And the fact that these compare so well, actually currently today the discrepancy is between the theory and observation is less than 0.01%. That's 1 in 10,000 of, that's what at least I read. So we can be pretty sure this is correct. And this experiment, along with the one I discussed last time or some time back about precession of perihelion, were the two signature experiments for GR. And they established not only that GR predicts correct answers, but that there is no competing theory, which is really complete. See, GR is complete in the sense all the rules have been told to you now. Anything in principle you can calculate. We didn't make up any new rules to calculate this. Okay, you might think we made up some new rules by changing from affine parameter, from proper time to affine parameter. I'll address that issue again tomorrow. It turns out that there's really no choice when we want to discuss light. And in any case, that rule didn't get used for precession of perihelion, only for this. But see, light experiments are much easier. You notice that, okay, they'd spend few months going and few months waiting there for the stars to be visible at night. But the previous thing, the precession, is some arc seconds per century. So that would take you a pretty long time to, not that you have to wait a century, but if it's few arc seconds in a century, you're not going to see it in 6 months or a year. You're going to see hundredth of even that effect. So this in a way you might say is easier. Because, and again, it only uses it uses both of course used only telescopes. That was all used. Okay, so tomorrow at 10 we'll meet and we'll talk about gravitational redshift and time.